Okay, so let's take a few moments here. We'll look at some problems. We're still solving problems that are with objects that are in equilibrium, or in other words, when F net is equal to 0. This is page 237. We're going to have a look at questions 1, 2, 3, and 4 here. A guy wire with a tension of 1 times 10 to the 4 newtons and an angle of 60 degrees from the ground is attached to the top of a hydroelectric pole as shown in figure 711. What are the horizontal and vertical components of the force exerted by the wire at the top of the pole in order to maintain the system in static equilibrium? Let me just draw a diagram here. 60 degrees. And 1 times 10 to the 4, or 10,000 newtons, which seems like an awful lot of force, doesn't it? And the question is, what are the horizontal and vertical components of the force exerted by the wire at the top of the pole in order to maintain the system in static equilibrium? So all they're really asking for is what? They're asking for that and that, right? So it's just trigonometry, right? Do I even need to do this one? Ty is going to be 10,000 sine 60, and Tx is going to be 10,000 cos 60, whatever those work out to be. I may even have these answers somewhere. Yes, I do. The x is 5,000. And the y is 86, 60.3 newtons. So, like, really, are you going to expect to see a lot of questions like that? No. That's just a warm-up, right? Yeah. Child's play, if you will. Go. Oh yeah, let's move on to number 2. Sorry about that little interruption. What does number 2 say? This time we've got a canoe is tethered to a car with ropes shown in figure 712a. What is the tension if in the vertical rope, if junction assumed to be massless is held at static equilibrium by the 2 lower ropes, each with a tension of 100 newtons? And the picture of the actual car doesn't really do a whole lot of good, really. Yeah, I would agree. So let's just redraw this free body diagram here. 140. 100 newtons, 100 newtons, and they really want to know what is the tension in the vertical rope. So really they're just asking for T. What is your plan of attack? First of all, let's remember that the overall net force in all dimensions is 0, right? So could it just be 200? It sure would be nice if it was just 200, wouldn't it? But it's not. No. How come? How come, Chris? We've got to count for the directions, right? It's very similar to the ones where the people were weighing on the wires at an angle, right? You had to do the weight scale. Very similar to that. So really what we're saying is, if I call this one, let's call this one T1, and I'll call this one T2, and this one will just be T. So T1Y plus this one here, T2Y, have to add up to the actual value of the tension, right? So really all I have to do is figure out what this T1Y is. Is T2Y going to be exactly the same? Yes. And then multiply by 2, right? So it's really, when you sort of boil it down, it's not that hard. So I'm going to put a little dot there, and those are equivalent. If this is 140 degrees in here, right, a straight line is 180 degrees, which means I've got 4, let's just write it down here. 180 minus 140 is 40 degrees, and then 40 divided by 2, of course, is 20. So these are 20 degrees in there, right? From some, I don't even know, when do they teach you that math now? The whole geometry, angle stuff. Remember? 9 or 10 trig? Okay, so 20 degrees. So really, let's deal with T2Y because it's a little bigger and a little cleaner here. I got more room. So opposite hypotenuse. So Sine of 20 is my opposite. T2y over my hypotenuse, which is 100. T2y is 100 sine 20. And I get 34.2. All right? And then you would say something like t is equal to, well, t1y is also equal to 34.2. So t is equal to 34.2 plus another 34.2, or 68.4 newtons. Let's just drew the free body diagram to make sure that we're on the right track here. Bag of clothespin is hung in the middle of a 3-meter long clothesline. Cause the line to dip 1.5 degrees below horizontal at each end. So if it was strung perfectly straight, it would be 3 meters long, but it's not. Right? So it's actually like, and I'm going to exaggerate the angle. Right? So 1.5, right? Now, where is the 1.5 degrees below horizontal at each end? Unfortunately, it's 1.5 again, right? So it'd be that angle in there. Would that be the same as that angle right there? It would indeed, wouldn't it? So there's A. Are you ready for B yet, or do you want to try? So part B, is it even asking for a force in part B? What's it really asking? How far does the center of the line dip? So they're really just asking for, can I call it X? Call it whatever you want, I guess, really. Eh? They're just asking for that side there. If this angle is 1.5 and that hypotenuse is 1.5, this is opposite, so it's going to be sine of 1.5 is equal to opposite, which is X, over hypotenuse 1.5. Solve for X. 1.5 times the sine of 1.5, and I get 0.0393 meters, or 3.9 centimeters. Question C just asks, what is the mass of the bag of clothespins if the tension in the line is 85 newtons? Okay, so I'm going to redraw. This is with length, so I really should sort of redraw it for a force one. And again, I'm exaggerating the angle. So the bag of clothespins, no, the tension is 85. Now, is that 85 here and 85 there? Yeah, and this always gives us grief. The way I read it, that's 85, right? The tension is the same whether it's one side or the other, right? The tension is 85. So if that's 85, what is the mass of the clothespins? If that's 85, then this we'll call this Ty, which I know you can solve for. Again, opposite over hypotenuse. So sine of 1.5 is opposite Ty over 85. 85 sine 1.5. 2.23. Now, that's just the vertical component on one side, right? That's just this side over here. This side over here has another one, right? So that means that the weight force of the bag of clothespins is actually 2.23 plus another 2.23, right? And now how do I get the mass of the clothespins? Fw is equal to mg. 4.46, we're solving for mass. Gravity is 9.8. And I get 0.455 kilograms. I would step that up on the challenge scale a little bit, right? I understand that how much tension is a bit of a sticking point there. Okay, and maybe you didn't get the diagram drawing quite right. Just you got to read it a little more carefully. I'll pause for a second. Here's number 4. Forces can also be applied by compressing or tensing a rigid object such as a beam. And this is one of the things that those civil engineers spend hours and hours and hours studying. 2 beams support a 4 kilogram pail of water above an open well, I'll show in figure 713. So let's just draw this. Okay, and I'm just going to draw it very simple. 4 kilograms, 1.3 meters, and 1.9 meters. And the question is, how much compression force is exerted on each beam by the water pail? So compression force is like the opposite of tension. Tension is stretching apart, right? Compression force is the opposite. Now, wires will break if you stretch them far enough, right? If the tension becomes too much. Will beams break if you compress them too much? Absolutely, right? And that's something that engineers need to know how to do. So this is a great example of, these are the kind of questions, if you're taking civil engineering first year, this is what you're going to see. How much compression force is exerted on each beam by the water pail? Hello, Mr. Thacker. Okay, so basically think of it as compression, or think of it as tension, just sort of the opposite way kind of thing, right? So they want to know if I could even, how do we want to label compression? I mean, so we use T for tension, right? I guess you could use big C for compression. I don't know. Can we just call it, just seems weird to do that. Can we just call it force? It's a compression force? Sure, right? You can label whatever you want, right? Some prof's going to probably call it something different later. So compression force. What's the one thing that's not given? Any angle. So how are we going to solve this? Can we get an angle? Yeah, actually relatively simple, right? We've got this height here. We've got half, we can figure out what halfway is, and so you could figure out, basically you could figure out what that angle down there is, right? That triangle there goes in there, right? Okay, so what's halfway of 1.3? Is it 0.65? Right? Come on, you guys. 1.3 divided by 2. 0.65, right? 1.9. You guys got to give me some feedback, because I don't know whether I'm just boring you or you don't get it. Or you get it and you're, just stop talking. I need some feedback. So what's the angle? Inverse tan, right? Opposite over adjacent. 1.9 over 0.65. I get 71 degrees. Would it? It would have to be, right? Because what's the other half bottom? Well, the height is the same, and the other half means equal, right? So yes, it would have to be the same old stats, right? And I know, Brandon, you want to look at one that's got different ones. We'll have to find one like that. Okay, so 71 degrees. So really, what's my next step now? Like, what's contributing to this force, this compression force? There's a vertical compression, right, which is being produced by this, right? And because of that angle, there's also an outward force. And so I really just need to I need to redraw this diagram with 71 degrees in there. What's the force, the y component here? Well, it's 4 kilograms pulling down times 9.8, but also divided by 2 because there's 2 sides, right? So this Fy here is actually 4 times 9.8, but divided by 2 because there's 2 of them. Or 19.6 newtons, right? There's 19.6 newtons on each beam of vertical compression. Yeah. Well, we're going to do, the question says how much compression is there in each beam, right? If we do 1, the other one's going to be the same. I divided by 2 because the 4 kilograms is shared. Half, 2 kilograms on the left beam, 2 kilograms on the right beam. So now what is my Fx? Now here, I don't know the hypotenuse. Here I only know opposite, right? And I need to find adjacent, and I know the angle. So it's going to be tangent of 71 is equal to opposite 19.6 over adjacent Fx. I get 6.7. Right? What are we trying to solve for, friend? The compression force, right? Now remember, these are these force vectors? Like this is 19.6 newtons in which direction? Let me put it in red. Down, right? And this is 6.7 newtons. If I'm doing the one on the left, it's to the left. But what I'm really interested in is that direction there. How do you add those two? You just 19.6 plus 6.7? You got to add the directions. They're vectors, right? So what is it? It's 19.6, 6.7. You got to solve for compression force there, that hypotenuse. FC squared, 6.7 squared, plus 19.6 squared. I get 20.7 newtons of compression.
Did you get 6.7?
Do I need to write one more step down here? I went, Fx is equal to 19.6 divided by tan of 71. Right? The Fx and the tan 71 just switch spots. So there it is, the answer to B. I think B is how much compression force there is it not? How much compression force exerted on each beam by the water pail? 20.7. And they would be rated to a certain amount of compression. And C, I think we've already done. What outward force do the two beams exert on the well's wall? Outward force. How much are they pushing out? Well, aren't they talking about the Fx there? Okay, outward force. 6.7 newtons. Now, how come I solved it in B and then just write it down in C? Is there an alternate way that we could have gotten this 20.7? Yeah, absolutely. Because I've got this 19.6 here, right? I've got the angle. Could I not have solved, instead of here solving for Fx, couldn't I have solved for the hypotenuse? Absolutely, right? So I didn't really need to do this step, did I? But I would have had to do it in part C. Yeah. Right? I could have solved for the hypotenuse here. Yep. No. Well, it depends because, I mean, if the beam is at an angle and it's the hypotenuse of the triangle, then it will be, right? But if it's a straight up and down beam, right? Like, for example, if you go back to question number 1, here, right? There's actually, remember the guy wire thing, right? There's actually compression on this pole, right? That's equal to Ty, right? Because the wire is actually pulling the pole straight down in the ground. So that would be that thing there. So in answer to your question, no, compression is not always going to be like
What's the additional?
Say that again?
C says what additional vertical compression is exerted on the bricks under the beams? What is that?
What additional vertical compression is exerted on the bricks? Additional. Oh, I guess, would it be the weight of the beams as well? I think, is that what they're,
I guess it's just a word.
I have here, my answer key says, since vertical compression on the bricks is down 19.6 newtons each, but it says what additional vertical compression?
So what is the because you said 6.7.
No, 6.7 is, oh, C was the, oh, that's B, right?
Oh,
Yeah, that's B. I guess that whole thing was A. I thought I was doing, this thing is B, right? This is the outward one, right? I just mislabeled that. This was all A, right? Yeah, just B there. I don't know, Jake, that's weird, eh? What additional, what does the answer in the back say? Can you find it? My notes say 19.6, but it says additional vertical compression. It says 19.6? Yeah.
Horribly written.
Yeah, oh, it is. Yeah, I agree. But would you agree that the additional compression, like if you want to say additional, it would be the weight of the beams, would it not?
That would make sense.
I would say so. And it would be, it would actually, it would only be the vertical component of the weight of the beams, right? And the horizontal component of the weight of the beams would be in part B, wouldn't it? Yeah. Whatever. I'm not going to worry about it. That's a bit of a challenge question, there's no doubt about that, right? We'll go with 19.6, because that's what the book says, although we're not sure if we agree. Okay, there are some more, if you're interested, more textbook questions. Where did I write those down? I think it's page 267. I'm going to give you time to work. So page 267, you can try 18 to 25. Of course, they're textbook ones, so they're at your own risk.